Hello everyone, it's Caller from 19. Today's day 25 in my challenge today. And what I'm going to do is it's the last week of this course and it's about batch normalization. I think so. Batch normalization and merge class classification. I think I can't do merge class classification today. I've tried to end batch normalization. And let's start.
In the rise of deep learning, to in the rise of deep learning, one of the most important ideas has been an algorithm called batch normalization, created by two researchers, Sergei Ioffe and Christian Szegedy. Batch normalization makes your hyperparameter search problem much easier. It makes your neural network much more robust to the choice of hyperparameters. There's a much bigger range of hyperparameters that work well, and it'll also enable you to much more easily train even very deep networks. Let's see how batch normalization works. When training a model, such as logistic regression, you might remember that normalizing the input features can speed up learning. So you can compute the means, subtract off the means from your training set, compute the variances, this sum over xi squared, this is a element y squaring, right? And then normalize your data set according to the variances. And we saw in an earlier video how this can turn the contours of your learning problem from something that might be very elongated to something that is more round and easier for an algorithm like gradient descent to optimize. So this works in terms of normalizing the input feature values to a neural network or to logistic regression. Now, how about a deeper model? You have not just input features X, but in this layer you have activations A1, in this layer you have activations A2, and so on. So if you want to train the parameters, say W3, B3, then won't it be nice if you can normalize the mean and variance of A2 to make the training of W3, B3 more efficient? In the case of logistic regression, we saw how normalizing x1, x2, x3 maybe helps you train W and B more efficiently. So here the question is, for any hidden layer, can we normalize the values of A, let's say A2 in this example, but really any hidden layer, so as to train W3, B3 faster? Right? Since A2 is the input to the next layer that therefore affects your training of W3 and B3. So this is what batch norm does, batch normalization, or batch norm for short does. Although technically we'll actually normalize the values of not A2, but Z2. There is some debate in the deep learning literature about gamma and B3 faster, right? Since A2 is the input to the next layer that therefore affects your training of W3 and B3. So this is what batch norm does, batch normalization, or batch norm for short does. Although technically we'll actually normalize the values of not A2, but z2. There is some debate in the deep learning literature about whether you should normalize the value before the activation function, so z2, or whether you should normalize the value after applying the activation function, a2. In practice, normalizing z2 is done much more often, so that's the version I'll present and what I would recommend you use as the default choice. So here is how you would implement batch norm. Given some intermediate values in your neural net, let's say that you have some hidden unit values z1 up to zm, and this is really from some hidden layer, so it'd be more accurate to write this as z for some hidden layer I for I equals 1 through m, but to reduce writing, I'm going to omit this square bracket L just to simplify the notation on this slide. So given these values, what you do is compute the mean as follows. Again, all this is specific to some layer L, but I'm omitting the square bracket L. And then you compute the variance using pretty much the formula you would expect. And then you would take each of the zi's and normalize it, so get zi normalized by subtracting off the mean and dividing by the standard deviation. For numerical stability, we usually add epsilon to the denominator like that, just in case sigma squared turns out to be 0 in some estimate. And so now we've taken these values z and normalized them to have mean 0 and standard unit variance. So every component of z has mean 0 and variance 1. But we don't want the hidden units to always have mean 0 and variance 1. Maybe it makes sense for hidden units to have a different distribution. So what we'll do instead is compute. For numerical stability, we usually add epsilon to the denominator like that, just in case sigma squared turns out to be 0 in some estimate. And so now we've taken these values z and normalized them to have mean 0 and standard unit variance. So every component of z has mean 0 and variance 1. But we don't want the hidden units to always have mean 0 and variance 1. Maybe it makes sense for hidden units to have a different distribution. So what we'll do instead is compute, we call this z tilde equals gamma zi norm plus beta. And here, norm gamma, we call this z to have a different distribution, mean 0 and variance 1. Maybe it makes sense, but hidden units to always have mean 0 and variance 1. Maybe it makes sense, but hidden units to always have mean 0 and variance 1. Maybe it makes sense, but hidden units to have a different distribution. So what we'll do instead is compute, we call this z tilde equals gamma zi norm plus beta. And here, gamma and beta are learnable parameters of your model. So if you're using gradient descent or some other algorithm, like the gradient descent with momentum or RMS prop or atom, you would update the parameters gamma and beta just as you would update the weights of your neural network. Now, notice that the effect of gamma and beta is that it allows you to set the mean of z tilde to be whatever you want it to be. In fact, if gamma equals square root sigma squared plus epsilon, so if gamma were equal to this denominator term, and if beta were equal to mu, so with this value up here, then the effect of gamma z norm plus beta is that it would exactly invert this equation. So if this is true, then actually z tilde I is equal to zi. And so by an appropriate setting of the parameters gamma and beta, this normalization step, that is these four equations, is just computing essentially the identity function. But by choosing other values of gamma and beta, this allows you to make the hidden unit values have other means and variances as well. And so the way you fit this into your neural network is, whereas previously you were using these values z1, z2, and so on, you would now use z tilde I instead of zi for the later computations in your neural network. And we want to put back in this square bracket L, to explicitly denote which layer it is in. You can put it back there. So the intuition I hope you'll take away from this is that we saw how normalizing the input features X can help learning on a neural network. And what Bash norm does is it applies that normalization process not just to the input layer, but to the values even deep in some hidden layer in the neural network. So you apply this type of normalization to normalize the mean and variance of some of your hidden units values Z. But one difference between the training input and these hidden unit values is you might not want your hidden unit values to be forced to have mean 0 and variance 1. For example, if you have a sigmoid activation function, you don't want your values to always be clustered here. You might want them to have a larger variance or have a mean that's different than 0 in order to better take advantage of the nonlinearity of the sigmoid function rather than have all your values be in just this linear regime. So that's why with the parameters gamma and beta, you can now make sure that your zi values have the range of values that you want. But what it does really is it ensures that your hidden units have standardized mean and variance, where the mean and variance are controlled by two explicit parameters, gamma and beta, which the learning algorithm can set to whatever it wants. So what it really does is it normalizes the mean and variance of these hidden unit values, really the zi's, to have some fixed mean and variance. And that mean and variance could be 0 and 1, or it could be some other value, and it's controlled by these parameters, gamma and beta. So I hope that gives you a sense of the mechanics of how to implement Bash norm, at least for a single layer in a neural network. In the next video, I want to show you how to fit Bash norm into a neural network, even a deep neural network, and how to make it work for the many different layers of a neural network. And after that, we'll give some more intuition about why Bash norm could help you train your neural networks. So in case why it works still seems a little bit mysterious, stay with me. And I think in 2 videos from now, we'll really make that clearer. So you've seen the equations for how to implement Bash norm for maybe a single hidden layer. Let's see how it fits into the training of a deep network. So let's say you have a neural network like this. You've seen me say before that you can view each hidden unit as computing 2 things. First, it computes Z, and then it applies the activation function to compute A. And so you can think of each of these circles as representing a 2-step computation. And similarly for the next layer, that's Z2, 1 and A2, 1, and so on. So if you were not applying Bash norm, you would have an input X feed into the first hidden layer and then first compute Z1. And this is governed by the parameters W1 and B1. And then ordinarily, you would feed Z1 into the activation function to compute A1. But what we'll do in Bash norm is take this value Z1 and apply Bash norm, sometimes abbreviated Bn to it, and that's going to be governed by parameters beta 1 and gamma 1. And this will give you this new normalized value Z1. And then you feed that to the activation function to get A1, which is G1 applied to Z tilde 1. Now you've done the computation for the first layer, where this Bash norm step really occurs, in between the computation from Z and A. Next, you take this value A1 and use it to compute Z2. And so this is now governed by W2, B2. And similar to what you did for the first layer, you would take Z2 and apply it through Bash norm. I'm going to abbreviate that BN now. This is governed by Bash norm parameters specific to the next layer, so beta 2, gamma 2. And now this gives you Z tilde 2, and you use that to compute A2 by applying the activation function, and so on. So once again, the Bash norm step kind of happens between computing Z and computing A. And the intuition is that instead of using the unnormalized value Z, you're going to use the normalized value Z tilde. That's in the first layer. In the second layer as well, instead of using the unnormalized value Z2, you're going to use the mean and variance normalized values Z tilde 2. So the parameters of your network are going to be W1, B1. It turns out we'll get rid of the B parameters, but we'll see why in the next slide. But for now, imagine your parameters are the usual W1, B1 through WL, BL. And we've added to this neural network additional parameters, beta 1, gamma 1, beta 2, gamma 2, and so on, for each layer in which you are applying Bash norm. For clarity, note that these betas here, these have nothing to do with the hyperparameter beta that we had for momentum or for the computing the various exponentially weighted averages. The authors of the Adam paper had used beta in their paper to denote that hyperparameter. The authors of the Bash norm paper had used beta to denote this parameter, but these are two completely different betas. I decided to stick with beta in both cases in case you read the original papers, but the beta 1, beta 2, and so on that Bash norm tries to learn is a different beta than the hyperparameter beta used in momentum and in the Adam and RMS prop algorithm. algorithms. But so now that these are the new parameters of your algorithm, you would then use whatever optimization you want, such as gradient descent, in order to implement it. So for example, you might compute d beta L for a given layer, and then update the parameters. Beta gets updated as beta minus the learning rate times d beta L. And you can also use Atom or RMS prop or momentum in order to update the parameters beta and gamma, not just gradient descent. And even though in the previous video I'd explained what the Batch norm operation does, computes means and variances and subtracts and divides by them, if you're using a deep learning programming framework, usually you won't have to implement the batch norm step or the batch norm layer yourself. In some of the programming frameworks, it can be sort of one line of code. So for example, in the TensorFlow framework, you can implement batch normalization with this function. We'll talk more about programming frameworks later, but in practice, you might not end up needing to implement all these details yourself, but it's still worth knowing how it works so that you can get a better understanding of what your code is doing. But implementing batch norm is often, something like one line of code in the deep learning frameworks. Now, so far, we've talked about batch norm as if you were training on your entire training set at a time, as if you were using batch gradient descent. In practice, batch norm is usually applied with mini batches of your training set. So the way you actually apply batch norm is you take your first mini batch and compute Z1, same as we did on the previous slide, using the parameters W1, B1. And then you take just this mini batch and compute the mean and variance of the Z1s on just this mini batch. And then batch norm would subtract by the mean and divide by the standard deviation, and then rescale by beta 1, gamma 1 to give you Z1. And all this is on the first mini batch. Then you apply the activation function, to get A1, and then you compute Z2 using W2, B2, and so on. So you do all this in order to perform one step of, say, gradient descent on the first mini batch, and then you go to the second mini batch, x2, and you do something similar, right? Where you now compute z1 on the second mini batch, and then use batch norm to compute z1 tilde. And so here in this batch norm step, you'd be normalizing z tilde using just the data in your second mini batch. So this batch norm step here is looking at the examples in your second mini batch, computing the mean and variances of the z1s on just that mini batch, and then rescaling by beta and gamma to get z tilde, and so on. And you do this with the third mini batch and keep training. Now, there's one detail to the parameterization that I want to clean up, which is previously I said that the parameters was WL, BL for each layer, as well as beta L and gamma L. Now, notice that the way ZL is computed is as follows. ZL equals WL times A of L minus 1 plus B of L. But what batch norm does is it's going to look at the mini batch and normalize ZL to first have mean 0 and standard variance, and then a rescale by beta and gamma. But what that means is that whatever is the value of BL is actually going to just get subtracted out, because during that batch norm normalization step, you're going to compute the means of the ZLs and then subtract out the mean. And so adding any constant to all of the examples in a mini batch, it doesn't change anything because any constant you add will get canceled out by the mean subtraction step. So if you're using batch norm, you can actually eliminate that parameter. Or if you want, think of it as setting it permanently to 0. So then the parameterization becomes ZL is just WL times AL minus 1, and then a rescale by beta and gamma. But what that means is that whatever is the value of BL is actually going to just get subtracted out. Because during that batch norm normalization step, you're going to compute the means of the ZLs and then subtract out the mean. And so adding any constant to all of the examples in a mini batch, it doesn't change anything because any constant you add will get canceled out by the mean subtraction step. So if you're using batch norm, you can actually eliminate that parameter. Or if you want, think of it as setting it permanently to 0. So then the parameterization becomes ZL is just WL times AL minus 1, and then you compute ZL normalized, and when you compute Z tilde equals gamma ZL plus beta, you end up using this parameter beta L in order to decide what's the mean of Z tilde L, which is what gets passed to the next layer. So just to recap, because batch norm zeroes out the mean of these ZL values in the layer, there's no point having this parameter BL, and so you might as well get rid of it, and instead is sort of replaced by beta L, which is a parameter that controls, that ends up affecting the shift or the bias terms. Finally, remember that the dimension of ZL, because if you're doing this on one example, is going to be NL by 1. And so BL had dimension NL by 1 if NL is the number of hidden units in layer L. And so the dimension of beta L and gamma L is also going to be NL by 1 because that's the number of hidden units you have. You have NL hidden units, and so beta L and gamma L are used to scale the mean and variance of each of the hidden units to whatever the network wants to set them to. So let's put it all together and describe how you can implement gradient descent using batch norm. Assuming you're using mini batch gradient descent, you iterate for t equals 1 to the number of mini batches. You would implement forward prop on mini batch xt, and doing forward prop in each hidden layer, use batch norm to replace ZL with Z tilde L. And so this ensures that within that mini batch, the values Z end up with some normalized mean and variance. And the values and the version with the normalized mean and variance is this Z tilde L. And then you z tilde L descent using Bash norm. Assuming you're using mini Bash gradient descent, you iterate for t equals 1 to the number of mini batches. You would implement forward prop on mini batch xt, and doing forward prop in each hidden layer, use Bash norm to replace zl with z tilde L. And so this ensures that within that mini batch, the values z end up with some normalized mean and variance. And the values and the version with the normalized mean and variance is this z tilde L. And then you use backprop to compute dw, db for all the values of L, d beta, d gamma. Although technically, since we've gotten rid of b, this actually now goes away. And then finally, you'd update the parameters. So, w gets updated as w minus the learning rate times this as usual. Beta gets updated as beta minus the learning rate times dB, and similarly for gamma. And if you've computed the gradients as follows, you could use gradient descent. That's what I've written down here. But this also works with gradient descent with momentum, or RMS prop, or atom, where instead of taking this gradient descent update, you could use the updates given by these other algorithms, as we discussed in the previous week's videos. So these other optimization algorithms as well can be used to update the parameters beta and gamma. You've seen me say before, you gets updated, or atom, where instead of taking this gradient descent update, you could use the updates given by these other algorithms, as we discussed in the previous week's videos. So these other optimization algorithms as well can be used to update the parameters beta and gamma that Bash norm added to your algorithm. So I hope that gives you a sense of how you could implement Bash norm from scratch if you wanted to. If you're using one of the deep learning programming frameworks, which we'll talk more about later, hopefully you can just call someone else's implementation in the programming framework, which will make using Bash norm much easier. Now, in case Bash norm still seems a little bit mysterious, if you're still not quite sure why it speeds up training so dramatically, let's go to the next video and talk more about why Bash norm really works and what it's really doing. So why does Bash norm work? Here's one reason. You've seen how normalizing the input features, the x's, to mean 0 and variance 1, how that can speed up learning. So rather than having some features that range from 0 to 1 and some from 1 to 1,000, by normalizing all the features, input features x, to take on a similar range of values, that can speed up learning. So one intuition behind why Bash norm works is this is doing a similar thing, but for the values in your hidden units and not just for your input layer. Now, this is just a partial picture for what Bash norm is doing. There are a couple further intuitions that will help you gain a deeper understanding of what Bash norm is doing. Let's take a look at those in this video. A second reason why Bash norm works is it makes weights later or deeper in the neural network, say the weights for layer 10, more robust to changes to weights in earlier layers of the neural network, say in layer 1. To explain what I mean, let's look at this motivating example. Let's say you're training a network, maybe a shallow network like logistic. regression, or maybe a neural network, maybe a shallow network like logistic regression, or maybe a deeper network on our famous cat detection task. But let's say that you've trained your data set on all images of black cats. If you now try to apply this network to data with colored cats, where the positive examples are not just black cats like on the left, but to colored cats like on the right, then your classifier might not do very well. So in pictures, if your training set looked like this, where you have positive examples here and negative examples here, but you were to try to generalize it to a data set where maybe the positive examples are here and the negative examples are here, then you might not expect a model trained on the data on the left to do very well on the data on the right, even though there might be the same function that actually works well, but you wouldn't expect your learning algorithm to discover that green decision boundary just looking at the data on the left. So this idea of your data distribution changing goes by the somewhat fancy name covariate shift. And the idea is that if you learn some x to y mapping, if the distribution of x changes, then you might need to retrain your learning algorithm. And this is true even if the function, the ground truth function mapping from x to y remains unchanged, which it is in this example because the ground truth function is this picture a cat or not? And the need to retrain your function becomes even more acute, or it becomes even worse if the ground truth function shifts as well. So how does this problem of covariate shift apply to a neural network? Consider a deep network like this, and let's look at the learning process from the perspective of this hidden layer, the third hidden layer. So this network has to learn the parameters W3 and B3. And from the perspective of the third hidden layer, it gets some set of values from the earlier layers and then has to do some stuff to hopefully make the output y hat close to the ground truth value y. So let me cover up the nodes on the left for a second. So from the perspective of this third hidden layer, it gets some values. Let's call them A21, A22, A23, and A24. But these values might as well be features, x1, x2, x3, x4. And the job of the third hidden layer is to take these values and find a way to map them to y hat. So you can imagine doing gradient descent so that these parameters w3, b3, as well as maybe w4, b4, and even w5, b5, maybe trying to learn those parameters so the network does a good job mapping from the values I drew in black on the left to the output values y hat. But now let's uncover the left of the network again. The network is also adapting parameters w2, b2, and w1, b1. And so as these parameters change, these values a2 will also change. So from the perspective of the third hidden layer, these hidden unit values are changing all the time. And so it's suffering from the problem and B, as well as maybe W. The third hidden layer is to take these values and find a way to map them to y hat. So you can imagine doing gradient descent so that The network does a good job mapping from the values I drew in black on the left to the output values Y hat. But now let's uncover the left of the network again. The network is also adapting parameters W2, B2, and W1, B1. And so as these parameters change, these values A2 will also change. So from the perspective of the third hidden layer, these hidden unit values are changing all the time. And so suffering from the problem of covariance shift that we talked about on the previous slide. So what batch norm does is it reduces the amount that the distribution of these hidden unit values shifts around. And if we were to plot the distribution of these hidden unit values, maybe this is, technically we normalize a z, so this is actually z21 and z22, and I'm just going to plot two values instead of four values so we can visualize it in 2D. What Bashnorm is saying is that the values for z21 and z22 can change, and indeed they will change when the neural network updates the parameters in the earlier layers. But what Bashnorm ensures is z22 can change, and indeed they will change when the neural network updates the parameters in the earlier layers. But what Bashnorm ensures is that no matter how it changes, the mean and variance of z21 and z22 will remain the same. So even if the exact values of z21 and z22 change, their mean and variance will at least stay, say, mean 0 and variance 1. Or not necessarily mean 0 and variance 1, but whatever value is governed by beta 2. And gamma 2, which if the neural network chooses can force it to be mean 0 and variance 1, or really any other mean and variance. But what this does is it limits the amount to which updating the parameters in the earlier layers can affect the distribution of values that the third layer now sees and therefore has to learn on. And so Bashnorm reduces the problem of the input values changing. It really causes these values to become more stable so that the later layers of the neural network has more firm ground to stand on. And even though the input distribution changes a bit, it changes less. And what this does is even as the earlier layers keep learning, the amount that this forces the later layers to adapt to its earlier layers changes is reduced, or if you will, it weakens the coupling between what the earlier layers parameters has to do and what the later layers parameters have to do. And so it allows each layer of the network to learn by itself, a little bit more independently of other layers. And this has the effect of speeding up learning in the whole network. So I hope this gives some better intuition, but the takeaway is that batch norm means that, especially from the perspective of one of the later layers of the neural network, the earlier layers don't get to shift around as much because they're constrained to have the same mean and variance. And so this makes the job of learning in the later layers easier. It turns out batch norm has a second effect. It has a slight regularization effect. So one non-intuitive thing about batch norm is that each mini batch, say mini batch xt, has the values zt, has the values zl scaled by the mean and variance computed on just that one mini batch. Now, because the mean and variance computed on just that mini batch, as opposed to computed on the entire data set, that mean and variance has a little bit of noise in it because it's computed just on your mini batch of, say, 64 or 128 or maybe 256 or larger training examples. So because the mean and variance is a little bit noisy because it's estimated with just a relatively small sample of data, the scaling process, going from ZL to Z tilde L, that process is a little bit noisy as well because it's computed using a slightly noisy mean and variance. So, similar to dropout, it adds some noise to each hidden layer's activations. The way dropout adds noise is it takes a hidden unit and it multiplies it by 0 with some probability and multiplies it by 1 with some probability. And so dropout adds multiplicative noise because it's multiplying by 0 or 1, whereas batch norm has multiplicative noise because it's scaling by the standard deviation, as well as additive noise because it's subtracting the mean. Where here, the estimates of the mean and the standard deviation are noisy. And so similar to dropout, batch norm therefore has a slight regularization effect. Because by adding noise to the hidden units, it's forcing the downstream hidden units not to rely too much on any one hidden unit. And so similar to dropout, this adds noise to the hidden layers and therefore has a very slight regularization effect. Because the noise added is quite small, this is not a huge regularization effect, and you might choose to use batch norm together with dropout, and you might use batch norm together with dropout if you want the more powerful regularization effect of dropout. And maybe one other slightly non-intuitive effect is that if you use a bigger mini batch size, right? So if you use a mini batch size of, say, 512 instead of 64, by using a larger mini batch size, you're reducing this noise and therefore also reducing this regularization effect. So that's one strange property of dropout, which is that by using a bigger mini batch size, you reduce the regularization effect. Having said this, I wouldn't really use batch norm as a regularizer. That's really not the intent of batch norm, but sometimes it has this extra intended or unintended effect on your learning algorithm. But really, don't turn to batch norm as a regularization. Use it as a way to normalize your hidden units, activations, and therefore speed up learning. And I think the regularization is an almost unintended side effect. So I hope that gives you better intuition about what batch norm is doing. Before we wrap up the discussion on batch norm, there's one more detail I want to make sure you know, which is that batch norm handles data one mini batch at a time. It computes mean and variances on mini batches. So at test time, you're trying to make predictions, trying to evaluate the neural network. You might not have a mini batch of examples. You might be processing one single example at a time. So at test time, you need to do something slightly differently to make sure your predictions make sense. In the next and final video on batch norm, let's talk over the details of what you need to do in order to take your neural network trained using batch norm to make predictions. Batch norm processes your data one mini batch at a time, but at test time, you might need to process the examples one at a time. Let's see how you can adapt your network to do that. Recall that during training, here are the equations you'd use to implement batch norm. Within a single mini batch, you'd sum over that mini batch of the zi values to compute the mean. So here, you're just summing over the examples in one mini batch. I'm using m to denote the number of examples in the mini batch, not in the whole training set. Then you compute the variance, and then you compute z norm by scaling by the mean and standard deviation with epsilon added for numerical stability. And then z tilde is taking z norm and rescaling by gamma and beta. So notice that mu and sigma squared, which you need for this scaling calculation, are computed on the entire mini batch. But at test time, you might not have a mini batch of 64, 128, or 256 examples to process at the same time. So you need some different way of coming up with mu and sigma squared. And if you have just one example, taking the mean and variance of that one example doesn't make sense. So what's actually done in order to apply your neural network at test time is to come up with some separate estimate of mu and sigma squared. And in typical implementations of batch norm, what you do is estimate this using a exponentially weighted average, where the average is across the mini batches. So to be very concrete, here's what I mean. Let's pick some layer L, and let's say you're going through mini batches x1, x2, together with the corresponding values of y, and so on. So when training on x1, for that layer L, you get some mu L. And in fact, I'm going to write this as mu for the first mini batch and that layer. And then when you train on the second mini batch, for that layer and that mini batch, you end up with some second value of mu. And then for the third mini batch, in this hidden layer, you end up with some third value for mu. So just as we saw how to use an exponentially weighted average to compute the mean of theta 1, theta 2, theta 3 when you are trying to compute a exponentially weighted average of the current temperature, you would do that to keep track of sort of what's the latest average value of this mean vector you've seen. So that exponentially weighted average becomes your estimate for what the mean of the z's is for that hidden layer. And similarly, you use an exponentially weighted average to keep track of these values of sigma squared that you see on the first mini batch in that layer, sigma squared that you see on the second mini batch, and so on. So you keep a running average of the mu and the sigma squared that you're seeing for each layer as you train the neural network across different mini batches. Then finally, at test time, what you do is, in place of this equation, you would just compute z norm using whatever value z you have and using your exponentially weighted average of the mu and sigma squared, whatever was the latest value you have, to do the scaling here. And then you would compute z tilde on your one test example using that z norm that we just computed on the left and using the beta and gamma parameters that you had learned during your neural network training process. So the takeaway from this is that during training time, mu and sigma squared are computed on an entire mini batch of, say 64, 128, or some number of examples. But at test time, you might need to process a single example at a time. So the way to do that is to estimate mu and sigma squared from your training set. And there are many ways to do that. You could, in theory, run your whole training set through your final network to get mu and sigma squared. But in practice, what people usually do is implement an exponentially weighted average, where you just keep track of the mu and sigma squared values you're seeing during training and use an exponentially weighted average, also sometimes called a running average, to just get a rough estimate of mu and sigma squared. And then you use those values of mu and sigma squared at test time to do the scaling you need of the hidden unit values z. In practice, this process is pretty robust to the exact way you use to estimate mu and sigma squared. So I wouldn't worry too much about exactly how you do this. And if you're using a deep learning framework, they'll usually have some default way to estimate the mu and sigma squared that should work reasonably well as well. But in practice, any reasonable way to estimate the mean and variance of your hidden unit values z should work fine at test. So that's it for batch norm. And using it, I think you'll be able to train much deeper networks and get your learning algorithm to run much more quickly. Before we wrap up for this week, I want to share with you some thoughts on deep learning frameworks as well. Let's start to talk about that in the next video.
Before I'm going to end up this recording, let's recap fast because we don't have any time. So what I learned today is about batch normalization. And the advantage of this batch normalization technique is we can make hyperparameter search more easier so that we can make our model to learn faster. And and it also enables us use to much more easily train very deep networks is us. In the previous week, we saw an input normalization here um, by dividing up inputs with its standard deviation so that we can these circle shaped with circle shaped distribution instead of that these elongated contours. So our question is that can we normalize these each activation layers to train for next parameters faster? It's about because we need to use these techniques in the deep neural network so we can uh, we should answer this question. So and this is exactly what batch normalization does. So to implement batch normalization, shortly batch norm from now on, we have an intermediate values in neural network. Let's call it is GI. To normalize GI, we need to first compute the mean and the variance and get a normalized G. And we should know that we added an epsilon in the inside of square root because for numerical stability, because the inside of square root can be a zero. So it doesn't make sense in our implementation. So we need to add a slight value as an epsilon. But we don't always want the hidden units to have mean zero and variance one. So for different distribution, we modify the equation a little bit by multiply normalized z with the gamma and plus beta. So we use always z as a parameters of activation functions in the networks, but now we use these g tilde as the input parameters of the activation functions. The feeding to batch normalization into neural network follow these steps. So I think it's already mentioned in the previous sections. And to adopt this concept in the mini batches, we do the same things for each mini batches, but the different part is that we calculate the whole mean and the whole variance from the batch side. But in this case, we compute the mean and variance for only for the specific mini batch. So in this case, we have some noise in the mean and variance because every mini batches has a different input training samples. So it can be have a different mean and variance, obviously. So to implement gradient descent in mini batches, let's assume that we have a number of mini batches which is equal to m. So we iterate the mini batches 1 to m and compute for the propagation on current mini batch T. And for each hidden layer in the mini batch, use batch normalization to replace ZL with the G tilde L. And then we calculate the back propagation to compute by computing the dWL, d gamma L, and d beta L, which is the d gamma L and d beta L is a new parameters by adding from the batch normalization and update parameters with the user formulas we already used before. And we also can use the optimization algorithms like momentums and RMS probe and ADAM algorithm for obtaining parameters, regardless of using the batch normalization. And why batch normalization works? Let's assume that we have a black box in the left side of the network, And to compute the what the third layer, this the third layer does that to take the activation in the previous steps and then map try of find a way to map them to the y hat, which is a prediction. But if we uncover the black box, we can see that it also has a parameters that impacts on the previous activations before the third layer. So if the input parameters can changes before the activation second activation, it can also changes. So this is called covariance shift, and the covariance shift is can be explained this example. So we train the model with various real photos about the animals, and we want to classify whether an image is a cat or not. But and in the test set, our classifier is required to classify an image whether it is a cat or not, but the image is about cartoon. Trivially, this doesn't work well because our model learned real image like real cat and real dog, but test set is a cartoon. So difference in bit distribution between training and testing set is called a coverage shift. Also in our neural network example, so if we change this, uh, the W and WB by updating each of them in the learning steps, it can be changed. The value can be changed. But what the batch norm does by learning the gamma and beta, we want to keep the mean 0 and variance 1, even though we take a several steps in the learning. So we can just keep the distribution between the values. There is an unintended side effect on in batch normalization. So we got to know that we can use the batch normalization in mini batches, and the mean and variance it depends on the certain mini batches. But at the test time, we only test on example from the whole examples. So in this case, um, it can be quite uh, ridiculous that predict predict our output by the one example. So we can take a concept of exponentially weighted averagism here. So if we map to each layer of mean and variance to theta 1 and theta 2 and so on, like I already did in the London temperature example, and at the test time for a test example, we can apply the estimated mean and variance by exponentially weighted average. Let me see. Yes, like these examples, we can take on averages. If we gave a much higher beta, we can take on a lot of averages the previous days. So, so this is the end of today's recording, and thanks for watching.